Go. Hello and welcome back to Calculus 2, section 10.5 on comparison tests. On the sheet I distributed, you have comparison tests all the way on the bottom. I like to call these last resort tests, okay? When everything else fails, it's comparison tests that, might help you survive through the problem. And that's the reason why they are listed at the end. That's the reason why I distribute this chart larger than the chart that it's in your book. The order in which this chart is presented is really cool, the best order I have seen. So we have two comparison tests. One is called direct comparison, and the second one is called limit comparison. 90% of the time, it's a limit comparison test, and then rarely direct comparison. So we are going to start with what we call direct comparison test. And this is the one, as I said, that it's not used a lot. And it goes like this. For two sequences that are positive, if an is less or equal than bn and summation of bn converges, the summation of an converges as well. These are infinite series. So this is part one. And then part two, if an is bigger than bn and summation of bn diverges, the series summation an diverges. That's it. So that's your test, and this is the cloud. So you will find this on line number 9 on your sheet. Now, much better to understand these tests is if you look at the graphs. So for number 1, I am going to have, this is n, right? This is an axis. I am going to have in black some crazy an that I can't really, get a good grip, at. So the black ones over here are an. So my job is to find the bigger converging bn, and you can see that the black sequence, whose series we don't know what's happening, is getting squeezed in between the convergent sum of bn and 0. So it has to converge because it's getting squeezed into it, right? So this is the convergence one. And you see that your comparison will be like that. And now for number 2, which is the second line in the cloud, we have the opposite thing. Your ends again. So now you still have this an that it's all over the place, right? You can't put your finger on it, but then you're able to find a series sequence Bn whose series diverges, and then that one will push the An into divergence. So those two are now represented graphically, and I hope you understand it from there. Now the problems look a little bit weird, but we should make it. Let's first see this. Summation of sine n divided by n squared, let's say from 1 to infinity. You can start at 30 if you want, I don't care. You can't start at 0 because n squared, right? So what should we do here? Well, we know that sine n is bounded by 1, right? So I can compare to 1 over n squared. And what do I know about 1 over n squared? Yes. Summation of 1 over n squared converges by p series. Last class we said if p, which is the 2 in this case, if p is bigger than 1, it converges. And now we conclude that summation of sine n over n squared converges. So why does it converge? Because 1 is bigger than the sine. And because 1 is bigger than the sine, that is our condition that condition on a Bn, and then we have convergence. So it kind of squeezes it into convergence, and we have a convergent series. Let's take a look at another case. I might have to change the sign. Let's say infinity 3 over n minus 1. I might have to change to n plus 1. We'll see. Just be ready to change the problem. So what do I have? I'm going to compare this. So my an is 3 over n minus 1. I know that I can kick these 3 in front of the sum, and I will have 1 over n minus 1. This n minus, the minus 1 is what's messing things up, because if it was 1 over n, we know its harmonic divergence, we're done. But that minus 1 over there prevents us from using integral test. Or we could use integral test. But you can now say Bn is 3 over n. And you know that summation of 3 over n diverges by harmonic. So need to show the condition. If you are able to do this proof, if this condition holds, then your summation an will automatically diverge. Oh, sorry, not that. For divergence, this one. Circle the wrong one. For divergence. So I need to show that an is bigger than bn. Need to show an bigger than bn. So plug them in. 3 over n minus 1 needs to be bigger than 3 over n. Cross multiply, you get 3n larger than 3n minus 3. That's true. So we have divergence. So we can write, since an is bigger than bn and summation of bn diverges, summation of 3 over n minus 1 diverges by direct comparison test. These are all infinities, obviously. 1, 1, so on. So that's, you have to do the proof. This proof over here is the heart of this test. I'll need to come up with more of these examples. Look at the tricky ones. But first, let's take a look at another easier test. Say you have summation 2 to infinity, whatever, and you have n divided by, n plus 1, let's say, divided by n cubed minus n, whatever. So that one should be also one of the easier ones. Are you expecting convergence or divergence looking at the form of the question? What does this, if you look from far away, what does this problem look like? When you look at the stuff from far away, that means that you kill the stuff that doesn't contribute as much as the front values. So what does it look like? It looks like 1 over n squared when you cancel it, whose summation converges by p series. So now need to show that an is smaller than bn, because bn is convergent one and you want to squeeze an into convergence. So now you do the proof, and if that condition holds, then you are done. We might have to switch some stuff, but so try the proof. You have your an, you have your bn. Try to run the inequality proof. So my an is n plus 1 over n cubed minus n. Should be less than equal than 1 over n squared. So now I'm going to cross multiply. I'm going to get n cubed plus n squared, which should be smaller than n cubed minus 1. What happened?
N cubed minus n over n cubed minus
n. N cubed, oh, n cubed minus n over here. Okay. So that's going to be n cubed minus n over here. Yeah, it doesn't work. How do I fix this? I fix it by changing this into a minus. I didn't have the problems ready, so they're ready now, but if I do that, so that would fix the issue here, and then we're good to go. All right, perfect. There we go. So just by changing that plus on top into a minus, we have the problem fixed. So again, it's kind of hard to come up with the examples for direct comparison. This test is not used a lot, because limit test obviously is much better. Oh, no, not done yet. So this holds now, because when you cancel n cubes, right, move n squared to the other, because they're negative, right, it turns out to have n less equal than n squared, and we know n is a positive number, so that holds for all positive numbers. So we're good, right? And we can say, since an is less equal than bn, and summation bn converges, the series summation n minus 1 over n cubed minus n converges by direct comparison. That's the answer. Box that, and you're done. So for the direct comparison, guys, you have to pick the sequence such way, usually p series and so on. We'll do that again for the limit. And then you have to do the proof. It's either an or bn needs to be bigger, depending which way the problem goes. Let's take a look at the limit test, and then we'll do more examples. Limit comparison test. Now this is the biggie, right? This one is the big one. There is also the more advanced version of this in advanced calculus, if you ever take it. And for this test, you will be using the limit. This is the last row of your sheet. So again, for an and bn larger than 0, if the limit n goes to infinity of an divided by bn is finite number larger than 0, and summation of bn converges, the summation of an converges as well. We don't care where it starts. Just make sure the denominators are not 0. Now, if limit an of bn equals to L larger than 0 and bn diverges, then series an diverges as well. There are more conditions than this, but these are sufficient actually. Your book lists even more stuff, but these are sufficient.
Limit to any towards infinity, right?
Both limits are n, yes.
Okay.
The entire chapter is n goes to infinity, because we are dealing with infinite series, right? So all of the limits will be going to infinity. Awesome. So let's pick up something from over here. What was our problem up there? Aha. So let's say you want to test 1 over n squared plus 4. The gut feeling on this is convergence because of 1 over n squared. So you are comparing it to 1 over n squared because that's the form of your problem once you kill off the non-important stuff, right? So we know that the summation of 1 over n squared converges by p series. And now we crank the limit of an over bn. An is 1 over n squared plus 4 divided by 1 over n squared. And when we deal with a double fraction, we get n squared divided by n squared plus 4, which gives us 1. So both condition, we have a condition that this has to be a finite number, L, which is 1. That's awesome. And we have a convergence here. So now we conclude, since summation of 1 over n squared converges and limit an over bn equals 1, the series 1 over n squared plus 4 converges by limit comparison test. Again, what's in the red box, what's written in red is your answer. Everything prior to that is the partial credit. Spicier situation. Square root of k over k cubed plus 1 from 1 to infinity. So this is in a textbook. What do we compare this to? What would be my bn? What do you think? Okay, so now what? We're going to take it outside, or one wants 1 over k squared, the other one wants 1 over k. What is the non-essential thing that I have to kill?
Plus 1.
Plus 1. That's it. That's the only thing you can kill. Everything else is major, right? So when I kill plus 1, what is left?
1 over k squared.
1 over k squared. And what else is left? Square root of that. So square root of 1 is n, right? So 1 over k. 1 over k. So again, when we kill off the non-essential plus 1, then the stuff under the square root cancels down to 1 over k squared. Square root of 1 is 1. Square root of k squared, they cancel, and you just get k in the bottom. What do I know about 1 over k? Diverge. That's a harmonic series. It diverges. You can use either p series or integral test, whatever. Great. So now we have to make sure that the limit is finite. And if the limit is finite, we immediately claim divergence. So limit k goes to infinity of ak divided by bk. There we go. We need this to be finite. So limit k goes to infinity. And now I have the square root of k divided by k cubed plus 1 times k, right? Split. Now the k will go inside the root and pick up a square. And when it goes inside the root and pick up the square, it will make the k cubed. Exactly. So this becomes limit k goes to infinity, square root of k cubed over k cubed plus 1, which is 1. Because you have k cubed divided by k cubed, right? That's 1. If you divide everywhere by k cubed, you will get 1 divided by 1 plus 1 over k cubed. That goes to 0, and you just have square root of 1 divided by 1. So now we have the answer, since summation 1 over k diverges, and limit ak over bk equals 1. Series summation square root of k over k cubed plus 1 diverges by limit comparison test. That's limit comparison test. Let's take a look at another one. I have so many cool ones over here. All right. Let's do medium spice dish, and then we're going to do the hell on earth one. Summation 1 to infinity 1 over k times root k plus 2. So this should not be bad. Let's see what you come up with. No pressure. 18 seconds. Let's go. Can you at least tell me Bn?
1 over k to the 3 seconds, to the 3 halves.
Yes. Awesome. K to the 3 halves. You have k to the 1 times k to a half. The plus 2 is a non-essential thing that we kill, right, to come up with Bn. Now, does the series of this converge or diverge?
Converge.
Why?
P
P,
series.
yes, P series bigger than 1. Good. All right. Nice, nice. So, summation of 1 over k to the 3 halves will be convergent by P series. P, because P, 3 halves, is bigger than 1. Awesome. So all I need to do is to work out the limit. K goes to infinity. 1 over k square root k plus 2 divided by 1 over k 3 halves. This is going to be k to the 3 halves divided by the k times square root of k plus 2. There is the limit, k goes to infinity. One of the k's will cancel. So we will cancel this. We'll get k to the 1/2 left. So now we have limit k goes to infinity of square root of k divided by square root of k plus 2. Now, it's clearly 1, but let's work it out. Those of you who follow algebra, you know that you can combine this into a single square root. And then using more rules of limits, you know that you can kick exponent on the outside. Now you know that the limit inside is 1. So square root of 1, which is 1. And we can write the answer. Since Bn summation of Bn converges and limit, it's a k, bk. Since bk converges and limit ak over bk equals 1, k goes to infinity, the series summation 1 over k times square root of k plus 2 converges by limit comp test. Ta-da! One more, and we're done with these tests. Lock the doors. Infinity, so summation 2 to infinity. 1 over, open parenthesis, k times ln k squared. This ln k is going to make some noise now. So how are we dealing with this ln k? What's that comparable to? Does that graph look like anything else that we could use? The graph of ln x? This is the tough question, because if you don't know this, you clearly can't compare it to anything, and then you're just dead in the water. Does it look like anything? Square root of x. Very good. Is it perfect? No, right? It's not perfect. But are we looking for perfect? These are comparison tests. They just need to be close, right? So ln k will be compared to root k. And then you go from there. I'm just gonna play a little bit. Like if you really want to make it better for no reason, right?
Wait, so you take the ln of k and you replace it with a square root of f? Or you?
Well, what do you have? If you're going to write a comparison thing over here, right? You can say Bn is going to be 1 over k times root k squared, which is 1 over k cubed. Does this make any sense? And now summation Bn is summation 1 over k cubed convergent by P series. So this one is a tough one, but once you know the trick, now it becomes easy, right? Because now you know the trick that ln can be approximated by root n. I mean ln k, root k, whatever. So now we have to crank the limit. K goes to infinity. 1 over k times ln k all squared divided by 1 over k cubed, which is limit k goes to infinity, and we have k cubed divided by k squared ln squared k. This works out to be limit k goes to infinity of, when these guys cancel, k divided by ln squared k. And hello, L'Hopital rule, exactly. Beautiful. Do some derivatives. Have fun. So by L'Hopital rule, have limit k goes to infinity. 1 divided by 2 ln k times 1 over k. Ooh. this becomes limit k goes to infinity of k over 2 ln k. Now we still have infinity over infinity, so we do another L'Hopital rule, and that's going to be 1 over 2 1 over k, which is k over 2 with the limit in front, so we have infinity. So this might be the problem that we have to deal with using direct comparison. So here I'll write in blood, test is inconclusive. You must have a finite value. I don't care if it's 1 or 1/3 or pi. Your limit must be finite number. We got infinity. That means that this test cannot be used, limit test cannot be used on this problem. Now, the book did not sort the problems direct versus limit comparison. They just mushed all of the problems into one group, as you can see, and they said over there on the left, comparison tests. So I just picked 38 all the way on the bottom. They don't say which one it is. So we try the limit, because limit is the one that takes care of 90% of the problems, right? It didn't work. So now we have to go and try to solve this problem using the proof that Bn, right? So because the test was inconclusive, try direct comparison. Need to show for convergence, right? We need our Bn to be bigger than An to squeeze it. Need to show that Bn is bigger than An. So Bn was 1 divided by k to the 3, and that needs to be bigger than 1 over k ln k squared. So what do I have? Cross multiply k ln k squared needs to be bigger than k cubed. Remember that k is bigger than 0, can't be 0. Therefore, k squared ln squared k is it larger than k cubed? We can divide both sides because k can't be 0. Can divide both sides by k squared. And now we have ln squared k bigger or equal than k. What I'm going to do is I'm going to check this using graph, Desmos. ln, there are other ways. I just want to quickly check. ln x squared and x. So now this is what I have, and clearly x is black, so this doesn't hold. Inconclusive also. So we have two inconclusives. That means that we have to do better on the choice over here. the choice, unless I have, do I have any mistakes anywhere? I have this k cubed, k squared, that's a k over k. Take the derivative, 2 ln to the first, 1 over k. Let me see. What do I need? N divided by ln n squared Yep. So we have to do better on the choice. The choice was not good enough. Maybe we have to use that -1. And then that would help. So try again. So we have our AK to be 1 over k ln k everything squared, and then bk try 1 over k square root of k minus 1 squared. That's gonna add extra terms. That's going to add extra terms if I choose this way. So this should work now, because these two graphs we already showed, these two graphs are close. Well, sometimes it's sensitive. I mean, you know, such is life. 1 divided by, no coffee. Okay, no, x. Put the x there, close the parenthesis, and then put the division in. Okay, and over here, 1 divided by, why is that a p? Yeah, but it starts the one. And then we have x. X minus 1 to the 0.5, and then everything squared. Okay. So if we have this, maybe this will work. Let's work out this bk. So bk, we have 1 over k squared times, and when I FOIL this, I get k minus 2 root k plus 1 for the total of 1 over k cubed minus 2k to the 5 halves plus k squared. And maybe now do the comparison test or do the limit test. I don't know which one is worse. Let's try limit first. K goes to infinity. I'm going to use this form. So 1 over k ln k squared. Well, I'm just gonna separate those squares, so k squared ln squared k divided by 1 over k squared k minus 2 root k plus 1. When k squares cancel, we get limit k goes to infinity, and I get k minus 2 root k plus 1 divided by ln squared k. And then, without taking 15 L'Hopital's rules, I'm just going to cheat real quick over here so we don't spend all night doing this. I have k minus 2 square root of k plus 1 divided by ln k squared. Let's see, what do we get? We also get infinity, so test is inconclusive. So then we'll do the direct. So this was us trying the limit. Try the direct.
It was integral test.
Well, yeah, but it was in the comparison, so we should be able to figure out. Yes, it is for integral test because it's 1 over. No, actually, you can't because 1 over k squared. If you only had 1 over k, then it's integral test. It's 1 over k squared because everything is squared. So yeah, the power on ln doesn't matter, but the power on k does matter because you don't have. Not the limit now. Now need an to be smaller than bn. So bn needs to be bigger. I mean k. We're doing k's now. Okay, so what's my ak? It's 1 over n squared ln, no, it's k's. There we go, k squared. And that needs to be smaller than the bk, which is 1 over k squared k minus 2 root k plus 1. So what do we get? Cross multiply, k squared k minus 2 root k plus 1 needs to be smaller than k squared ln squared k. We are going to cancel k square, and now we have k minus 2 root k plus 1 needs to be smaller than ln squared k. Yeah, the graphing is the fastest way to do this. So what do I have? I have x minus 2 root x, 2 square root of x plus 1. So that's the top function is the blue, the green one. Really? Okay, and this one is ln of x squared, and the green is bigger.
Except for that smaller.
Yeah, it doesn't matter. The infinity later is much more important than what happens in a little. I'll have to meditate on this problem. Something is off over here. I'm not seeing something simple. I don't want to waste time because we still have to do alternating and then the review. So I will switch to the next section and I will have to see what is the issue with this. But We are supposed to compare ln k to square root of k, and for whatever reason it doesn't work with any of the two comparisons.
Can we use the squeeze theorem? Like it is less than 1 over n squared and greater than 1 over n cubed.
Well, you need one sequence. The theorem is about one sequence. That's the problem. So we'll figure it out. We'll solve it next class after the test. Let's just do the alternating series now because it's getting late.